We talked about different aspects of accommodation, the rate of accommodation, amplitude of accommodation. Right now, in this video, we want to talk about numbers actually. So as I mentioned before, during accommodation, our lens, when we are looking at far object, our lens is in the relaxed situation, that the radius of curvature is very big, like to flat surface, the radius of curvature is infinite. So in this case, our lens is very relaxed, but during accommodation, we remove the tension from our eye, and then make it accommodated. We make it more circular, and then it keeps the image at focus. So the amplitude of accommodation is the maximum potential increase in optical power that our eye can achieve during adjustment of the focus. And this parameter is a function of a lot of things. One of the most important one is aging. When you get older, your capability to do accommodation it decreased. So that's a very important concept that we're going to talk about it later. So lens design convention, always anything that is on the right hand side of the lens, we keep it positive, up positive, left hand side negative, bottom side is negative. So we keep this lens convention for actually solving our problem. So let's look at this imaging equation. We have this very well-known imaging equation, 1 over f plus 1 over object, this is the distance from object to the lens, is equal to 1 over image, the distance from the image to the lens. And 1 over f, in this case, we can replace it by optical power. Instead of that, we put f, which is capital F, optical power, plus 1 over O is equal to 1 over I. And now, when the object is at near point, our I optical power is at optical power of n, which is the near field, let's say optical power. When the object is at far distance, the optical power is f of f. But the image is always constant. That's the whole point of this process. The image is on retina. The distance from the lens to retina is not going to change. So that's something that we need to be very aware of that. Now let's look at an example. So here we have a kid that is looking at the cell phone at 10 centimeter, which is a really bad habit because put too much pressure on your eye. Another kid who is watching TV at 2 meter. So in this case, as I said, image is constant. Image is a retina, is always on retina, and that's a constant distance. So we just put I. But the change accommodate, the lens accommodate. So we put Fn for near distance, FF for far distance, object near, object at far. So based on this equation, we subtract these two equations from each other, and then we have Fn minus F plus 1 over n minus 1 over f. So we have this equation. Now, from this equation, actually we have this equation, and then we move them to the right. That's the reason we have negative sign. We have positive sign for 1 over OF. And delta F, which is Fn minus FF, is equal to this equation. So we should keep in mind this equation have a negative sign, 1 over On plus 1 over OF, if you want to memorize it. So we have this equation. Now, as I said, this side of the lens is negative, so negative 1 over, always for the optical power, diopter is 1 over meter. So you should change all the units to meter. Here is 10 centimeter, 0.1, we put 0.1 plus 1 over, because that's on the same side of the lens, negative 2. So at the end, we have negative cancel each other. We have 1 over 0.1, and actually it should be a negative sign here. So we have plus 10 minus 0.5, which is plus 9.5 diopter. So during this accommodation process, when you see an object at 2 meter, and then you see an object in 10 centimeter, we have 9.5 diopter accommodation. That's the amplitude of accommodation for these two objects, and this is how we actually calculate it. Thank you very much.